Hi, everyone, and thanks for joining us. We're going to give people just a couple minutes to get logged in, and then we'll get started. All right, it looks like several people have had a chance to log in, so we'll go ahead and get started. So hi, everyone. Thank you for joining us today. My name is Beth Neeser, and I'm going to be your host for our webinar, Optimizing Semiconductor Wafer Manufacturing with Proper Thermal Management. I'm joined by our two SwageLock speakers, Brian Rudary and Doug Nordstrom, who will be discussing ways that you can increase yield in your semiconductor wafer manufacturing processes by optimizing the thermal loop system. They're going to dive into some topics such as proper component selection, installation, and performance testing. Brian is a principal engineering lead and Doug is a senior product manager. And together they have nearly 40 years of combined experience here at SwageLock. If you have any questions throughout the presentation, please feel free to put them in the chat and we'll get to as many as possible at the end of the presentation. Any that we can't get to, we're going to be sure to have Doug or Brian follow up with you directly. So with that, I'm going to go ahead and hand it over to our presenters.
Thanks so much, Beth. And again, thank you everyone who's taking some time out of their day to join us for today's webinar. So Beth already mentioned some of the items we're going to talk about today, but just to share what our agenda looks like, we're going to highlight all of these forthcoming topics and covering all these in detail as we continue through the rest of today's webinar. However, before we get to the bulk of our content, I did want to share a little bit about SwageLock Company if you're not familiar with us. So at SwageLock, we recognize that every day our customers count on us to help them move fluid through some of the most critical applications that are on the planet. Doing this really is going to require support that's available around the world, around the clock, and most importantly, around the corner. That's why we've embraced a very unique global to local business model, one where we focus on high quality from the manufacturing side and connecting customers with the technical knowledge they need to overcome their toughest fluid system challenges. Alongside our 200 plus authorized sales and service center locations in over 70 countries, provide problem solving, local support, and timely solutions you need to maintain safe, efficient, and profitable operations. It's also important to highlight SwageLock's role within the semiconductor market itself. So SwageLock has been doing business internationally and on the global stage since the 1950s. And as a longtime leader of fluid system components and services, this also includes a host of semiconductor market innovations. SwageLock has products like our VCR fitting technology, which made its formal debut in the late 1960s, followed by more and different solutions that were intended to continue the pace of innovation within the semiconductor market. Today, SwageLock continues to focus on expanding our high purity manufacturing capacity with a workforce that is agile and well trained to meet the demands of the global business cycle. And like I previously mentioned, through our global network of authorized sales and service centers, we can really position ourselves and our experts to support customer needs all over the world. So getting into the heart of today's content. So as Beth had mentioned, we're talking a lot about thermal management today. And the first topic we want to cover is really to give a little more background around what that thermal loop or that thermal sub-process is and what we'll be talking about in a little more detail. So starting with some more background around what is this thermal loop that we're going to be continuing to mention. The thermal loop is the subsystem in a semiconductor fab site that provides the thermal needs of the wafer production process. Maintaining proper temperatures in semiconductor manufacturing is critical. with things like temperature fluctuations or the introduction of any contaminants and even moisture are a major concern that directly threatens the production process itself and can result in excessive downtime. Use of different solutions that are properly insulated and leak tight allows for consistent and for more repeatable performance across the manufacturing space. Maintaining thermal consistency is going to result directly to the output of that manufacturing tool. Any excessive temperature variations can increase scrap and downtime, with the consequence of failure there being potentially in the millions of dollars for subtle variations within temperature, so a lot to risk. It's also worthwhile to mention that you may have heard of this subsystem or this process described in other ways. You may have heard it more within respect to being called a thermal control loop, or even something more as simply as your cooling lines, your insulated hoses, and things of that nature. Just to share where this thermal loop subsystem is at within the fab site, we've got a nice cutaway here showing the different levels and areas within a fab site. You can see a cross section here with the typical areas, and that the clean room is going to be on the top floor there, the main primary fab floor. And that's where the fab process tools are going to be located and where the wafers are physically processed. Below that is our sub-fab area space, where you'll find all that different support equipment. Specifically, this is where the chillers are going to be installed, which is the heart and really a critical piece of our thermal loop subsystem. But it's more than just chillers, and there's more components down there that make this whole thermal loop a complete subsystem. So we've got a list here that are on the screen that really highlights what additional items you are going to be expecting to find within this area. And there's a few things here that are worth noting. It's really critical that these components are intended to meet the high demands of the subsystem space. So standard products such as fittings, valves, and hoses may not work for the ultra low temperatures that are experienced in this area. And that's why it's critical to utilize specialized components for semiconductor production. So continuing on, we've talked about insulation a little bit a few times. So we're going to dive in here a little more deeply into why is there a need to insulate some of these components within the thermal loop. And specifically, we're going to be talking about this with respect to the hose products that are within this subsystem. So we could really summarize this into 3 key points as to why it's so critical to insulate this part of our thermal loop subsystem. First and foremost, we want to make sure that we are enabling greater chiller efficiency. So our insulated hoses are going to boost that efficiency by ensuring stable temperatures. So we want to keep those temperature variations to an absolute minimum. And speaking of that thermal stability element is going to make sure that we're able to reduce heat loss and prevent condensation, which are both going to help make sure that we can preserve and maintain steady uptime within the fab processing site. And that preservation of that uptime is our last and final point we'd like to make, is it ensuring consistent temperatures, preventing equipment overheating, and reducing downtime due to thermal related failures. So all of these are key items as to why we find it so important to have to insulate some of these components, and specifically the hoses coming off of your chillers within the thermal loop. So Doug, I'll hand it off to you.
Thanks, Brian. So I'm going to dive into those 3 reasons a little bit in more detail. Starting with the improved chiller efficiency point that Brian made. So in this particular example, we've been lucky enough to have some users that have allowed us to study their thermal loop and determine the efficiency gains that properly insulated hoses provides. In this example that we did, the point of use temperature that this particular tool needed was minus 30 degrees Celsius. So the chiller's job, of course, is to start this coolant off at a temperature that will then provide that coolant at the tool at the point of use of minus 30 degrees Celsius. And this particular line was 40 feet long. So as we move away from the chiller, which is our x-axis in this case, when we get to 40 feet, that's where the particular tool is. We then, of course, have a return line that's also 40 feet. So after 80 feet of flow, we're back at the chiller. So again, the chiller line in this case needs to over chill the coolant down to minus 54 in order to get that coolant to the tool at minus 30. The coolant continues to warm as it goes back to the chiller and gets back to the chiller at about minus 6. So in this particular simple example, The chiller needs to do 48 degrees of chilling before that coolant can go back then to the tool. We consider this over chilling, and that's one of the efficiency problems that non-insulating hoses will result in. Let's see how I get this to go forward. Okay, there we go. So insulating a hose, what I call here heavy insulation or proper insulation, really decreases the amount of over chilling that a chiller needs to do. This same example, same flow rate, same media, point of use of minus 30 degrees Celsius. The chiller only needs to cool to minus 32, and the coolant then returns back to the chiller at minus 28. So it's really only doing 4 degrees of work, which is far better, of course, than the 48 degrees of work. Now, every chiller is different. Every installation is different. In this particular example, we were able to get some dollar values assigned to what this is, and every degree Celsius roughly resulted in 27 cents per hour of savings. So in this case, we are chilling or saving 44 degrees of over chilling, right? From the 48 with no insulation to only 4 degrees. So we're actually able to save, why am I not advancing? There we go. $11.88 per hour that this chiller is running. So every chiller is saving $11.88, which is, adds up in a hurry. So, sometimes we talk about what the cost of putting insulation on a hose could be. You end up making the savings back relatively quickly because you're saving so much on the chiller efficiency and reducing that amount of what we call over chilling. The second point Brian talked about was the thermal stability driving higher yield. Quite simply, thermal stability, predicting that minus 30 in the previous example and having that be stable is very important because gas molecules have a certain amount of energy at a certain temperature. And so as they flow through the chamber, we want to make sure that that energy within the gas going into the chamber is always consistent. It's very stable. And without that thermal stability, the chemical reactions that are going on inside the chamber are not predictable. So we want to make sure that's very predictable to drive higher yields. It's also very consistent across the entire surface of the wafer. And as we have uninsulated hoses or uninsulated thermal loops in general going through the fab, the amount of stability within the production is also going to go down. So this point of use temperature not only needs to be minus 30 to get the right reactions going on, but it needs to be very stable. And non-insulating a hose makes that temperature very unstable. Things like flow rate will have a major change in what that point of use temperature is. Things like room temperature are going to suck more heat or less heat out of the hose and have it be much less stable without insulation. But maybe most importantly, when a non-insulated hose is touching other things, so in this case, you can see it touches the floor the entire way. In Brian's pictures, it was touching different things as it flows from the chiller to the wafer fab. And that conductive heat transfer can be very unpredictable with a non-insulated hose. So the insulation itself makes that 30 degrees very, very stable and very predictable. That then drives up yield. Like Brian said, it can be millions of dollars of savings. Brian, I'm having trouble advancing. Maybe you could advance for me.
Sure thing.
Thank you. The last one that Brian mentioned is preserving uptime. Not only do we improve yield, but we want to improve uptime as well. And a lot of unplanned downtime is due to condensation dripping where it shouldn't be dripping, which is within the fab or even in the sub fab. This dripping is caused, it could be caused by leaks in one case, but in the case of uninsulated hoses, it's caused by condensation. And that condensation occurs because the air on the outside of the hose or surface cools below the dew point. And that colder air cannot hold the same amount of water vapor. This is what causes the condensation. Dew point is a function of air temperature and humidity. That condensation will continue to build just like it does on your glass on a warm summer day. It builds on a hose and it will continue to build until it drips and causes puddles, and it could be a potential leak. So this causes fabs to shut down and have to determine what the leak is. And this can be, very, very expensive downtime to have unplanned to figure out what this leak potentially could be within the clean room. So again, we want to make sure we eliminate planned downtime, and the best way to do that is to eliminate the condensation on hoses and the rest of the thermal loop. So now that we understand why we want to insulate the thermal loop, we want to talk about which product is right. There's a lot of different potential solutions. They offer a wide range of performance and at a wide range of prices. And so we want to make sure that we're speccing in the right product for the application. So I'm going to cover some very common products that we see. When we look at what our current customer needs are, we of course want to prevent condensation. That's one of the major issues that we're trying to do here. And the current temperatures that we see go down to about minus 65 degrees, and they go a little bit on the warm side in some cases, but for the most part we focus on the negative side. That's trending colder and colder, and what that's doing is it's driving us away from more flexible covers on hoses to different technologies. So industry shifts, what we're seeing is that these temperatures are going to minus 200 Fahrenheit, minus 120 or so C or colder. And what this is doing is it's driving us away from flexible cover insulations because they have a lower limit where they start to crystallize and turn into a poor insulator, and driving new technologies, things like vacuum barriers. And we're going to talk about some of these different products and why they work the way they do. So the first option is just a covered hose. So, Swagelok and other hose suppliers offer their hoses with silicone covers. The silicone cover actually acts as an insulator. It was originally designed to be a cleanable cover where you can wipe it down and make it clean, but it does act as an insulator. Very low temperature range, you can see it's not going to meet a lot of the needs, but about 0 degrees Celsius to 100 degrees Celsius. But the price is relatively small. It kind of comes along with the price of the hose. Very, very low price impact. But for very, very small temperature changes, this works really well at a very good price point. Fire jacket was the next thing used. Now, the fire jacket was originally designed to protect the hose from hot environmental temperatures or weld splatter, things like that. So it wasn't really intended to be an insulator, but we see more and more users applying this to hoses at hot temperatures. It's not intended to be a cold application, so for the thermal loop, it really isn't a factor, but it does do some insulating at higher temperatures. Again, very low price impact to put a fire jacket on the outside of a hose. Maybe one of the more common that we've been seeing, at least up until temperatures went below minus 10, are these foam covers because of the inexpensive nature of these. You can go to Home Depot or Lowe's or whatever hardware store and find these actually at the, for residential use, because they were designed to be put onto pipes in your house to keep the hot water hot as it went to your sink or your shower, whatever it might be. That was what they were designed for. And they're being applied to hoses more and more because of the low cost, but they're not really designed to do those kind of things. So we do want to cover that in a bit more detail soon here. But the most popular one lately has been this wrap insulation. And so this is an aerogel material wrapped onto hoses with a shrink wrap cover, and it really does the job for the current market demand for the thermal loop. It reaches temperatures of minus 60 up to about 125. It does cost more, so now we're getting to more expensive solutions here, but it does the job very, very well for the current market demand. Does an excellent job of insulating. It's very flexible, and it's meeting the needs. Now, the problem with it is, though, it starts to crystallize below minus 60. You can do some things to make it go a little bit lower, but as the market goes to minus 80, minus 100, minus 120, this material does not do a very good job insulating anymore because of the crystal nature that it becomes. And that's where we get into the latest technology. Vacuum layered hoses can really reach cryogenic temperature. These have been around for a while for cryogenic applications, not necessarily applied to the thermal loop as much, but we're seeing more and more interest in this because of the demand to go below minus 60. These can really go even below minus 253 C and up above 500 C. But again, you're getting into it now, the highest technology, best performing at the highest price. I did want to touch a little bit more on this foam wrap because we do see this causing issues more and more, especially in semiconductor applications, because it is not a flexible product. It can stay flexible for a while, but it has a tendency to start to dry out, deteriorate, and flake off. Of course, this would be very bad in a semiconductor fab. We've seen people put covers on it and things to collect the flaking, but even that does not really work well, because as it starts to deteriorate and flake off, it does not do nearly as well insulating. To make this also insulate better, you need to put more and more layers on this, and it becomes a very large footprint as well. So it takes up a lot of space, and it tends to have poor performance over time. It deteriorates.
And Doug, maybe if I could just add a quick comment there about this type of solution as well, is that, we mentioned a little bit earlier as we were starting, the importance of using products that are specifically designed and intended to be used in the semiconductor space in the specific application. And this is a great example of a solution that's fairly readily available, but has pretty much a wide variety of more residential or commercial uses than specific semiconductor ones. So just because it's available and just because it's low cost doesn't mean it's going to be the right solution. Just something to keep in mind for things that may be widely available on the open market today.
Exactly right. Yep. Thank you, Brian. So, labs, including Swagelok's lab, a lot of hose suppliers' labs, can do a lot of simple studies on how effective the insulation is. This is a picture we took in our lab here using a thermal camera to do different studies on how effective the insulation is, how it's going to perform with different media temperatures flowing through it, what happens when you bend the hose, what happens if you overcompress the insulation. Very similar to putting insulation in your walls. If you put too much or too little insulation, it's going to change their performance. There's a right amount that's going to maximize performance. And so all these types of things can be studied, and we can determine what's better for a particular application given the price of the insulation as well. We also do things like flow air across the hose, put fans on the hose, see how that changes the performance. And we could put all this into a calculator to help our users, our field engineers, determine what is the right insulation for a particular application, because we do want to be sensitive that we're not over providing too much insulation, and we certainly don't want to provide too little insulation. A lot of times if you provide a hose that does not have enough insulation on it, it gets installed, it starts to condense. There's not much more you can do other than buy another hose with more insulation. It's very difficult to put a different or more amount of insulation on a hose, so that could be just wasted hose at that point. So we want to make sure the right product is selected. This is a screenshot of our calculator. Other companies could have their own version, of course, but this is the one that we use. And it has various inputs that you see on the left, things like fluid temperature, relative humidity in the room, because we want to determine what the dew point is, which you see in the black line. The gray line on this calculator on the right, and the graph on the right, is an uninsulated hose. And the blue line is a hose with a certain amount of wrapped insulation. This is the version for our wrapped insulation product. And what our goal is here many times is to either determine if we're above the dew point line. Brian, if you could click, please. In this case, we want to see if we're above the dew point temperature for the thermal loop. That's what we're doing, because we want to make sure we eliminate condensation. But this hose can also be calculated to determine if the hose is safe to touch, which is on the right side of the graph. A typical safe to touch temperature is about 65 degrees C. So you can see the uninsulated hose becomes not safe to touch very, very quickly, because 65 is right around where I drew that arrow. So where's this hose going to remain safe to touch? On the hot side? But again, focusing back on the thermal loop, we want to see where's this hose going to start to condense. And in this case, this insulated hose never crosses the dew point line. So it really never will see condensation in this case, given the inputs I used. We can take our calculator for all these different types. I know there's a lot here on this graph, and we can see which is best for a particular application. So in this graph, you see here the uninsulated hose is shown in red through a wide range, wide temperature range. This particular one goes down to -200 C and up to 400 C. I stopped the different graphs of the other insulated materials at their insulation temperature range. So some of these lines are relatively short. Some of them are a bit longer. You can see as we go down on my list, which is more and more expensive, the line gets flatter and flatter. That's indicating better insulation at cold, right, and better insulation at hot. It's a better insulated solution. So the vacuum jacket, you can see, is relatively flat line. We stay relatively warm all the way down to minus 200 degrees C, and relatively cool, safe to touch at 400 degrees C. It's very, very hot, of course. So again, that's kind of, you get what you pay for. Now I wanted to focus in here on the thermal loop standard temperatures, at least the current market range of thermal loop standard temperatures, to see what those options look like. So that little dotted box is what I'm showing in this next graph here. And you can see the different options. The fire jacket starts at 0. That's the purple one I didn't mark. But the uninsulated, you can see, goes below a dew point, which is typical of maybe 12 degrees Celsius very, very quickly. It's going to have condensation very, very quickly. Where wrapped and vacuum jacketed really are your best solutions for staying above most dew points of about 12 degrees Celsius. So I wanted to talk a little, we've been talking about how superior the vacuum jacketed works. We wanted to really talk about why it works so well. Again, the market is using about minus 60 now is what we're seeing, and that's trending pretty quickly to minus 120 or maybe even colder within the next few years. So this is a pretty quick trend from what we've been seeing. And in order to reach that, we have to, what we're saying is here is eliminate convection heat transfer. There's 3 different heat transfer types: convection, conduction, and radiation. What we're doing with the vacuum layer is we're eliminating convection heat transfer. That's the heat transfer of through gases, right? If you heat up a fire on one side of the room, the other side of the room will get hot because of convection. So what we're doing here is we're eliminating any gases. So the inner hose is a standard metal braided hose. We have a outer hose, and in between there we pull a vacuum. So there's no more convection from the inner hose to the outer hose. And eliminating that convection really creates a superior performing product from the insulation standpoint. There's no more heat transfer from convection, there's almost no heat transfer from conduction, and there's no radiation going on. So we've essentially eliminated heat transfer, or very, very close to eliminated it. And again, the result is superior performance, minus 250 up to above 500 C. The last thing I want to cover before handing it back to Brian is I'm going to go through what to do with the hose once you select it, how to make sure we install this correctly so that you don't select the right hose and then everything goes wrong because hasn't been installed correctly. So again, step 1 is select the right hose, and these calculators and field engineers can help you do that if you desire. But we want to make sure that we consider everything available and select the right hose for the application. But then we need to make sure we route it correctly. Improperly routing hoses will cause a perfectly selected hose to fail. And what you see in this picture are really nicely routed hoses with nice long radius, some separation between the hoses, and it works really well for this particular application. So some considerations we want to look at. Most of these considerations are going to be revolving around getting new room temperature air to the surfaces of the hose. So the first one in doing so is we want to make sure there's some spacing between the hoses. You can imagine if 2 cold hoses, even if they're well insulated, were touching, it won't allow any new room temperature air to get to where they're touching, and even a nice insulated hose will end up getting cold spots, and that will cause condensation and cause essentially a failure of that installation. So we want to make sure they're spaced properly. We want to look for eliminating any real tight bends. Now, the official minimum bend radius of a hose does not change with insulation because we define that as when the hose is damaged. We're not going to damage the hose by bending it to its minimum bend radius, but we do change the performance of the insulation. So we want to talk about how that happens and what to look for there. And then lastly, not lastly, but the last one about airflow, getting air to the surfaces, what the airflow is in the room. And there's a coefficient here that we want to use when we do our calculator. And that's basically how much airflow is going through the room, the more the better, because that's easier to get the room temperature ambient air to the surface of the hose. And then lastly here is just what is the environment within the room. Many times a properly selected hose can fail just because it's in a rough environment, and controlling that environmental parameters, again, the dew point, which is a function of room temperature and humidity, can make a hose work that potentially would fail under different environmental conditions. So the first of those is the spacing. Again, it's critical to have this spacing so that you get new room temperature air to all surfaces of the hose. You see in the picture here that did not happen, and there's an ice ball between the hoses, so obviously there's condensation there. We have a rule of thumb, which is 3 times the OD is what we like to see. That allows air to get to all surfaces of the hose. It's a rule of thumb and not a rule, though, because of different things going on in the room. Different room temperatures could require more or less. Different humidity in the room could require more or less. And then also, of course, if you have a lot of airflow in the room, a lot of fans blowing on the hose, you can get away with very tight hose spacing. And because you're blowing and forcing new room temperature air to all surfaces of the hose with the fan. Then we talked about bending. This is one of the more difficult parameters or installation considerations to predict because it's not consistent. As we bend hoses, it stretches the insulation on the outside and it compresses the insulation on the inside. In both cases, what we're doing is we're squeezing the insulation material together, which is bad. It's similar to putting too much insulation in your walls of your house. That's actually a bad thing. You want the insulation material to be spaced and have some air gaps between it to stop the conductive heat transfer through the insulation material itself. You can see in these pictures here, the condensation, of course, starts and will always typically start at a bend because that's where the insulation material is not going to perform to the levels it will during a straight part of the bend. So there is no real way to calculate this. But the general rule of thumb that we use here is try to use 3 times the minimum bend radius, and the insulation should perform very close to the same level it will as a straight zone. So again, 3 times the spacing of the OD and 3 times the bend radius, the minimum bend radius of a non-insulated hose are rules of thumb for maximizing insulation performance. And then the airflow. This is the chart we use when we do our calculator. It's a bit difficult to measure, but what we're doing here is we're showing the heat transfer coefficient of air, and as a function of the velocity of air across a surface. So in a stagnant room with 0 velocity of air across a surface, we would use a heat transfer coefficient of 10, right where the y-axis is. If you had a large amount of velocity, a big fan flowing across the hose, you can use up to 35 there. So it's 3.5 times more effective. A lot of people don't put fans on the hose the entire way, so this can be very, very difficult to estimate. We typically use about 15 when we do our calculations, just because we want to assume on the conservative side that there's very little airflow in a room. When we measure this in our lab, it's very difficult to get below about 2 or 3 meters per second just in a standard room because of HVAC systems and things like that. So using a number around 15 is usually very conservative, but the point is putting a fan on a hose makes a huge difference. So again, closed spaces are where this becomes the most troublesome. Tight routings, but if a hose was in a very small closed space, we're going to use a number closer to 10. Using a number closer to 20 as if a fan is on the hose. But the point still being is these types of things are easier to control than many people think. Fans are relatively inexpensive, while insulating hoses can be relatively expensive. And so sometimes the most cost-effective way is to simply put some fans where the hose is flowing to, if at all possible. The last consideration here is just the environmental conditions. Of course, like I mentioned, room temperature and humidity drive our dew point line. So in this particular example, I'm showing an example where the point of use temperature is desired to be 45 degrees, negative 45 degrees. This hose that we're showing in our calculator has 6 layers of insulation wrapped around it, which is a lot. That's a lot of insulation. It's going to be a very costly hose. And it's crossing the dew point line. So this hose will likely condense, especially at any bends. This dew point line was calculated at 18 degrees C, so it's a relatively cold room, and also a high humidity. So one solution is to continue to wrap this hose, adding more and more cost into the hose. But a better solution here is let's put some environmental controls within the room. Let's warm up the room a little bit and maybe put some humidity control in there. So this same application, same inputs, other than what we're using to drive our humidity line, we raise the temperature to 23, which is a more standard room temperature, drop the humidity to only 40. And you can see we can now easily insulate this same hose with only 4 layers. So where a hose was failing with 6 layers before, we're now able to get a 4-layer hose to perform well, not condense, obviously at a lower price, and be much more, provide much more uptime without the condensation. Okay, I'm going to hand it back off to Brian now.
Yeah, great. Thanks, Doug. Yeah, so we've covered quite a bit of content here, from talking a little bit more about why it's so critical to insulate some of the products that we have on our thermal loop, kind of diving deeper into the whole hose world around it, talking about what the right product is, as well as the installation kind of considerations you have to take into account, which are all extremely critical, as Doug has kind of illustrated here as we continued through. I'm going to kind of bring us to the end here when we talk about more so at a wider lens, investing in the right relationships as you're seeking to continue to have optimal thermal management within your semiconductor fab. It's really important to partner with experienced providers who really understand the challenges you face within the semiconductor space. Like we just talked about today, expert component selection, cost reduction through more streamlined processes, and more advanced engineering tools enable right-sized solutions and are going to eliminate the guesswork and ultimately failure. So even by showing some of the examples that Doug had a few slides ago, showing how we can exactly pinpoint what the right solution is based on your environment and your manufacturing kind of environment, are all critical to make sure that guesswork's eliminated and you have the right solution each and every time. Now more than ever, the role of such partnerships are crucial in the semiconductor industry, which continues to be very fast-paced, and it continues to challenge more conventional norms. This not only refers to what the latest generation demands are for the producers of chips, but also where these activities are physically happening. As semiconductor manufacturing goes beyond its legacy epicenters around the world, it's important that an knowledgeable partner is available that can add value as semiconductor manufacturing evolves literally beyond its traditional terrain. We're a great example of that coming from you today in Northeast Ohio within the US. We're about 2 hours away from the Columbus, Ohio area where Intel is building its new fab site. Probably wouldn't have expected to see something like that pop up in Ohio 5 or even 10 years ago. So having that expertise globally available is even more critical as more and more semi-fab opportunities are popping up globally. And then what does that look like for the customer? What are the values and benefits there to having those kind of relationships? It's pretty straightforward. So really you're looking to reduce that downtime from having not only a reliable partner, but reliable components designed to meet the demanding needs of that environment. Increase semiconductor chip yields via that minimized thermal variation that we spoke about specifically with some of the hose options that are currently available, and more efficient media transfer. And then lastly, increased efficiency and reduced energy costs via improved chiller performance. So all of those align to be values and customer benefits as we talk about the added value of having those long-term partnerships with those who have that knowledge and expertise. So with that, concludes the content. So I think, Beth, if we had any, we've got some open time here for questions, so you can take it away.
Great. Thanks to both Doug and Brian for providing that information. So yeah, this time we're going to spend a little bit of time answering some of the questions that have come through during the presentation. I do see we had one that was answered and published, regarding the calculator. So that answer is in the chat. Some of the ones that haven't been answered yet. First of all, what are the options for a hose installation that ends up experiencing condensation after the install?
Yeah, you want me to take that one, Brian?
You feel free to start. I can add some color commentary.
Okay. So yeah, the best options, it's very difficult to take a hose and add more insulation. It's almost impossible. So the best options are to work with some of those environmental concerns I mentioned. Either try to reroute the hose so it can be spaced more, reroute the hose so it has a less of a tight bend, or see if there's possibilities of increasing airflow. maybe changing the humidity in the room. But really at that point, if a hose is installed and it has condensation, we're down to now the installation routing and controlling the environment around the hose are the really only two options.
Yeah, I would definitely agree with that, Doug. And if you're able to go through and start eliminating some of those factors, it could be a challenge, both the routing and the environment. It may end up being the wrong or a improperly used insulative property product is being utilized. So whether it's that foam wrap that we talked about, something that's available but not necessarily designed for more of the extreme environments. But Doug's point is definitely correct. Starting with some of those environmental factors to try and leverage what you're able to have without incurring any further downtime is always a encouraging start.
Great. Another one we have here, if hoses need to be routed tightly or within a confined space, how is condensation avoided?
Yeah, that's of course the tough one, and that does come up. A lot of times these semiconductor fabs, there's not a lot of space. The shadow of the tool, or whatever you might say, is not very large. And so what we see is that the vacuum insulation is by far the best. As you get higher and higher in your technology list, more and more expensive, these considerations that I mentioned come into play much, much less. In fact, we had our vacuum insulated hose and we were running liquid nitrogen at -200°C through the hose, and we had them bundled together, tightly touching, and we did not have condensation. So that's an example of where if you have some of these more difficult installations, you really need to go to the higher technology solutions in order to make sure that you avoid condensation.
Great, thanks. Hey, another question. How can tighter bends in the routing be handled by the calculator? How can I estimate the impact those routings will have on the performance of the hose?
Yeah, we're trying to actually work that into the calculator. What we're running into is as you bend tighter and tighter, it becomes less and less easy to predict. If you remember that picture I showed of the thermal view of the hose, the tight bends have a wide range of color, red to yellow, within there because it's harder and harder to predict. So right now we say that you can use the calculator to a 3 times the minimum bend radius. Once you go tighter than that, what we want to do is just add some buffer to that dew point line, and that our field engineers, as Brian answered in the chat, our field engineers have access to all these calculators, and they can help provide guidance as far as if you go tighter bend, they can suggest what kind of buffer is needed on that dew point line. But right now, what we simply do is assume the dew point is a little bit higher than what it actually is based on the inputs.
Okay. Great, thank you. That looks like those are all of our questions for today. So thanks again to Doug and Brian, and thanks to all of you for joining.
Yes, thank you, everybody.
Thanks, everyone.